Hi, my name is Laurent Kneip, and it is my great honor to present you our new 5-point minimal solver for event camera relative motion estimation. This is joint work between my lab, the Mobile Perception Lab at Shanghai Tech University, as well as the Robotics and Perception Group at the University of Zurich. Traditional approaches to visual odometry rely on feature extraction and matching, followed by the application of efficient geometric incidence relationships such as epipolar geometry or trifocal tensor geometry. Features may be given by either points or lines. Point feature extraction and tracking in event streams has already been proposed. Methods often rely on intermediate representations such as frames of accumulated events or the time surface map. These techniques produce frame-like images and thus let us reapply traditional image-based methods. However, it is intuitively clear that they are not as expressive as regular images, and it is neither clear which timestamp to assign to a feature nor how to properly describe them for the purpose of tracking or matching. A truly convincing traditional feature-based VO framework for event cameras remains yet to be shown. In man-made environments, events are predominantly triggered by high gradient appearance boundaries in the environment. Since many such boundaries may be straight, line features have become very popular in event-based motion estimation. They can seemingly be directly extracted by detecting planes in the original space-time volume of events. However, as we show in our work, the assumption of a planar distribution is incorrect. Indeed, the manifold location of the events is twisted, even in the case of pure translational displacements of the camera pose. We denote such a cluster an event tail, which is not just a linguistic play on the word event, but also a hint at the French word éventail, which means fan. Indeed, the sticks of a fan are twisting through space just in the same way a reprojected line does in the space-time volume of events. As we show in our work, under a locally constant velocity assumption, the event tail manifold can be parameterized by camera velocity and 3D line-related parameters. Feature extraction and motion estimation can hence no longer be separated, but need to be solved as a joint model-based clustering problem. We introduce the minimal form of the event tail manifold, which depends on line depth parameters as well as a partial relative velocity observation. The partial observability of the velocity is related to the aperture problem. The key to solve this problem consists of expressing the velocity in an intermediate line-dependent reference frame. The projected velocity variable has only 2 degrees of freedom, and we choose a 2-point, 2-plane parametrization for the 3D line. This results in 6 unknowns, and considering overall scale ambiguity, a minimal solver using 5 events can be created. We propose such a solver, which is automatically generated based on the Gröbner basis method. To round off our contribution, we propose a linear fusion strategy that merges partial velocity measurements from different line observations into one 3D velocity result. The correct functionality of the method is demonstrated on both simulated and real data, and, as shown in the beneath example, it is able to properly identify event tails and camera motion even in situations of extreme dynamics. Being the first event-based minimal solver, we believe that our work lays important foundational bricks towards a comprehensive geometric theory for event camera visual odometry. Through our most recent efforts, we have already been able to achieve speed-up factors of several orders of magnitude, and we see a path for this to become a highly embedded part of a truly event-driven visual odometry pipeline or novel 3D motion segmentation approaches. See the project webpage for further details.